Lecture 3. Hi, everyone. I'm going to show you this list again that we worked off of last time. Last time we took a look at the first 3 items, the quantities that we deal with in a circuit topology, and the 2 laws that govern how voltages and currents are related in a circuit. And today we are going to talk about the circuit elements, some of which we started talking about last week, in fact, but we'll go through everything, and many of which you have, again, seen or worked with in labs. Before doing so, though, I'd like to do an example of writing Kvl and Kcl, just so that we remember what we talked about last time, and also seeing an example. I'll say, so I'll just remind you that Kvl and Kcl consisted of this. Kvl said that the algebraic sum of all voltages across all the elements as you go around a loop, any loop in a circuit, is 0. Kcl stated that if you take any node in the circuit and you write the algebraic sum of all the currents going into the node, that sum is 0. Okay? And they are very powerful because, like I said at the end of last time, once you write all the KVLs and KCLs for a circuit, and of course, once you understand how each element works, for example, in a resistor, V equals Ri, and the equivalent of that for the other elements, once you have all these things, you can find out the solution to the circuit. You will have enough equations. So here I want to just go through an example of writing KVL and KCL. And I will do so without discussing specific elements. So I'll just use boxes to, oh, sorry about that. Where did it go? Oh, here. So I'll just use boxes like this. To represent these different elements that we are talking about. Without any particular emphasis on what each of these elements are, because I want to show the generality of the approach, regardless of what the elements are. Sorry, this is not being very cooperative today. Okay, so before I do it, I want you guys to take a couple of minutes, see if you remember how to write KVL and KCL, all the applicable KVLs and KCLs for a circuit like this, as a little exercise, and then we'll do it together. Okay? But remember that before doing that, you first have to give names to the voltages and currents of each element, right? And to do so, you also have to pick a polarity convention. So voltages and currents are properties that have a sense of direction or polarity. So give a name to each element's voltage and current, and write all the KVLs and KCLs. See if you can do it on your own. This is our first example, so you might not have seen things like this before, which is fine. Give it a little bit of a try, and then we'll do it together. Okay, maybe this is good enough. I mean, we don't need you guys to finish this right now. We will do it together, but I wanted you to have a little bit of a head start. So let's do it together. So I want to essentially solve this circuit, which means I have to write all my KVLs and all my KCLs, and of course, all the relationships that describe the elements, which we are not going to get into because we don't even know what these elements are. So for now, we are just concerned with KVL and KCL equations. And for that, I have to first define my voltages and currents. So I'll start, I guess I'm used to starting from the left, but there is nothing specific about that. I'll call this one V1, as in the voltage across element 1. And for its current, I'll choose this direction and call it I1. I could just as well have chosen a reverse polarity for the voltage and or a reverse polarity for the current. This is just a convention I'm setting up. I don't know a priori if this voltage really going to be higher on the top side. I don't know if in the manner I have defined it, once I solve the circuit, whether this voltage is going to be a positive number or negative number. So it's just something that I felt like doing. Put the plus sign on the top. Okay. Element 2, you could pick something else and call it element 2. I choose this one. And I just feel like calling this I2 in this direction rather than the other direction for no particular reason. Let's call this element 3, maybe like this. And I kind of felt like choosing that direction for I3. Maybe because for these two, I chose the direction of their currents to be going from the plus to the minus side. For this one, I thought, for a change, why not choose it the other way around? Yes?
Isn't choosing like separate directions for the current in the same branch like kind of contradictory?
So we have a question, isn't there a contradiction here where I have these two currents going in opposite directions, whereas they're in the same branch, right? That's the question.
You could say negative
Yeah.
I1 is I2, right?
Exactly. So that's a very good question and an even better answer. So in that case, I1 is equal to minus I2. But we'll get there systematically. You see, the point I'm trying to make here is I would like to ask that you guys, at this point, avoid the temptation to analyze things one step ahead. In other words, at this step, let's just give each element a name for the voltage and current. Okay? Let's not worry about what the relationships between these voltages and currents might be. We'll get to that in the next stage. I'm trying to build this up systematically, right? Once we gain enough practice for things of this nature, with things of this nature, then we'll be very much faster and do several steps maybe at once. But at this point, I don't want us to worry about what the KCL here implies or anything like that. I'm just putting down names. Okay, so 1, 2, 3. Let's call this 4. Like this, I4. And V5, I5. V6, maybe I6. V7, I7, I8, and V8, like this. So I've just chosen these and for no particular reason. So let's write KVLs. How many loops do we have in this circuit? So we have 3 that jump out. If you go around the whole thing, that's a 4th one. But you could perhaps also identify a 5th one here and a 6th one there, right? Now, not all these loops are going to give you independent new equations. So let's start with the ones that we know are going to be independent. So if I take these smaller loops, the ones that are empty inside, so if I write KVL for the one on the left, I have only V1, V2, and V3 involved. And clearly, there is not going to be any involvement from these other elements. And so that loop is going to be independent from this other loop that has these other elements. So I'm going to write these down. So my KVL equations so here's one loop. Let's call this loop 1. And I'm going to write KVL in the same manner that I did last time. Remember, my convention was when I go around the loop for each voltage, if I encounter the negative side of the voltage first, I will add a negative sign in front of it in my KVL equation. That does not imply anything about the voltage being negative. It's just what exists in KVL. So minus V1. Next, I come across, I'm going clockwise. So I come across V2, and I happen to hit the positive side first. So I'll include that with a positive sign. And finally, I have V3. And if I go clockwise, I'm encountering the negative side first. So minus V3. That's my KVL equation number 1. Let's take the second loop. Again, I like going clockwise. There's nothing special about that. So let's say if I start at the bottom left corner and I go clockwise, I encounter V3 hitting its positive side first, then the positive side of V6, then the positive side of V8, and then the negative side of V7. So I'm going to write things accordingly. So plus V3, plus V6, plus V8, minus V7. By the way, if you guys see I make a mistake, please let me know. And the third loop, so let's say I start at the bottom right corner. Going clockwise, I see the negative side of V6 first, so minus V6, then the negative side of V4, minus V4, and then the positive side of V5, plus V5. Yes. Can I write that down before I forget? And then, so minus V6 minus V4 plus V5 equals 0. All right? Mm-hmm. The question is if I prioritize having shorter equations and fewer equations, or fewer equations, and that's a very good question. The answer is neither. I don't prioritize anything. I'm trying to explore, to see how things look in a circuit. And again, prioritization is something that becomes a matter of art as you gain experience. When you see a circuit, you might recognize patterns. At this stage, I think if we try to do that, we might miss some fundamental points. So I'd rather not do anything. Having said that, there are 3 independent KVL equations in the circuit, and there is no way to have less than 3 KVL equations for a complete solution of the circuit. You actually do need 3 KVL equations. So even if you choose to, let's say, use these 2 and the big loop that goes around, you still need 3 KVL equations. No. There might be situations where you're trying to solve for one specific quantity or a few specific quantities in the circuit, and you might not need to use all the information contained in the circuit. And in those cases, yes, you might not need to write all the KVLs, and there might be 1 or 2 that happen to be more useful to you. Right? But for a complete solution of the circuit, you actually will need all the KVLs. So you're saying if in this case I had this loop and this other loop, in 2 equations I'd have all elements included. That's a very good observation. I'd have all the elements involved included, but I would not have all the information that the circuit has that relates all the elements. I would still need a 3rd equation. The number of required equations is equal to the number of unknowns that you have in a circuit. So in this circuit, we have 8 elements. Each has a voltage and a current. So that's 16 unknowns. So you need 16 equations for this circuit. Now we'll see how we get a bunch of them from KVL, a bunch of them from KCl, and a bunch of them from the element relationships. Now, let's work backwards one step. Each element a resistor, capacitor, or something, it will have a relationship that, a formula that connects its voltage and current, right? That's the identity of the element. So each element will at least give you one equation, right? So out of those 16 equations, 8 will come from the elements. So you need 8 for the number of KVLs and KCLs here, right?
So, KVL and KCL?
No. No. So we'll see here. So let's look at the KVLs here. So far, we have written 3 KVL equations, okay? Now imagine I take any other loop. So let's take the loop that is the combination of loop 1 and 2, okay? If I write that equation, it will have minus V1 plus V2 plus V6, plus V8 minus V7. You can see readily that if you add equations 1 and 2, that's what you get, because V3 will cancel out between the two of them. And you get the equation for the loop that's the combination of loops 1 and 2. So that's not going to be an independent equation. And similarly, if you combine loop 2 and 3, so if you go around the big loop that contains both 2 and 3, its equation will be the same as adding equations number 2 and 3 here, because V6 is going to disappear when you add the two sides of these equations. And if you add all 3 equations, V3 and V6 are going to both cancel out, and you're going to get the equation for the big loop going around. So none of these are going to give you a new equation. So let's go to KCL now, see what we can get from that. So KCL, how many nodes do we have here? So let's start indicating them. So this is one node. This is another one. This is another one. Another one. Another one. Another one. So 1, 2, 3, 4, 5, 6. Okay? So in principle, I should be able to write 6 KCLs. You might again guess that some of these might be redundant. In fact, remember I needed 8 equations. I already have 3. So I need 5 KCLs. The 6th one is going to be redundant. But let's write them. So bottom left corner, I'm going to write down the KCL equation for the bottom left corner. The algebraic sum of all the currents going to the node is going to be 0. Now there are 3 branches connected, means there are 3 currents. I1, if you look at the top, I1 going through the element number 1 is going down to this loop. So it's heading toward the loop, the way I have chosen its direction. So is I3, if you follow its path. And I7 is actually leaving the node. So if I write the algebraic sum, remember, again, my preference was when a current is indicated as heading toward the node, I include it with the positive sign. If it's indicated as being leaving the node, I include it with a negative sign. Okay? So let's write that down. So I have plus I1 plus I3 minus I7. Equals 0. The second node on the top left, I have I1 leaving it and I2 leaving it too. Now that at first might appear somewhat strange. How can I have 2 currents leaving it? But remember, I1 and I2 can both be either positive or negative numbers. Okay? So it's totally fine that the sum or that the sum of the 2 has to become 0. And in this case, according to my convention, because they are both indicated as being leaving the node, I have minus I1 minus I2 equals 0. Now if I go to the node in the middle at the top, I have I2 going into it, I3 leaving it, I6 leaving it, and I4 leaving it too. So I2 with a plus sign because it's going into it, minus I3, minus I6, minus I4 equals 0. And then the node at the top right, I have I4 going into it and I5 leaving it. So I have plus I4 minus I5 equals 0. Bottom right, I have I6 going into it, I5 going into it, and I8 going into it too. So all three with plus signs. Plus I5 plus I6 plus I8 equals 0. And finally, I have the node at the bottom where I have, at the middle, where I have I7 going into it and I8 going out of it. But if you count, we already have 8 equations here. So something suggests that that last equation that I just mentioned, which would be I7 minus I8, is actually redundant. It's not going to be independent of these other equations. And you can try that by adding up these equations, and you will see that things will cancel out. Not adding all of them maybe, but some of them, so that you get an equation that will work out to be I7 minus I8 equals 0. Okay, so I'm not going to write it. Okay. So what I just did, you might say, was a very systematic thing, in that I did not start by bringing in some insight into if this current is going this way, the other one should go the other way, and so on. I didn't show any preconception, if you want. I just said I'll give names to my voltages and currents, and I'll write the laws of the circuit, and things, and I will be confident that things will work out, okay, as long as I stay consistent and follow the rules. Now, this is 8 equations. So the above consists of 8 equations. You will get another 8 equations from each element. Each element has a relationship or some information about its voltage and current. We get another 8 equations from the, if you want, current voltage relationships. Oh, my computer is not cooperating today. It's sensitive. Of the elements. So in total, we have a system of 16 equations. The resulting system of 16 equations will give us all the 16 voltages and currents. Okay. There was a question here, I think. Yeah, so the question is, how would I spot which node would produce a dependent equation? The answer is the last one left. So I could take any 5 of these 6 nodes, and I would get 5 independent equations. There is nothing special about the bottom middle node. It just happens to be that I got there last. So I had already written 5 equations. But I could have written equations for all the nodes but the top right one. And then the top right one would be dependent. It would not be a separate equation. So you don't have to worry about which one. Same for the loops. You don't have to worry about which loops will give you dependent versus independent. Yeah. So you're asking how many KCLs and KVLs am I going to have so that I know if I have written them all or not, right? Now, I'm going to give you an answer, but a better answer, I think, is with experience. And that comes with practice and time. But here's one way to think about it. If you look at the circuit, all nodes but one. So you might say the case of KCLs is a little simpler, right? Because all nodes but one will give me an independent KCL equation, right? I got 5 KCL equations out of 6 nodes. And there's going to be one node that can be written as the combination of other equations, OK? So if I wanted 8 equations, I know I'm getting 5 out of KCLs. So I know I need 3 more that I'm going to get out of KVLs, right? So I'm saying by counting the number of nodes, it's easier maybe to see how many independent KCLs you have. And then based on that, you know how many independent KVLs you have. It's maybe harder to tell by looking at it how many independent KVLs you have at the beginning, right? Now, I don't want to get into circuit topology too much and formulas about if you have such and such circuit graph, how many KVLs and KCLs and so on. I'd rather we get used to it with experience. But in simple terms, that's how you can think of it. Right? So again, if I wanted to work backwards, I have 16 unknowns. I have 8 elements, so each of them will give me one relationship. And I have 6 nodes, out of which I'll get 5 KCLs. So I'm left with finding 3 equations. Those inevitably have to be KVLs. Okay. I'm sure there are other questions. Questions are good. Don't be shy to ask questions. Okay. Discussion. If anything, asking a question is great service to, I think, to class, because it can be very monotonic. 2 hours, one person in the afternoon. So it's definitely yes. Thank you. The calculator question came up again. Okay. So let me give an extreme example. Am I going to give you a circuit that has 100 equations and ask you to solve it in 5 minutes without a calculator? No. When you say this much equations, so for this particular circuit, the number 16 might sound daunting, right? A system of 16 equations and 16 unknowns, especially if each of the 16 equations included all 16 unknowns, would be quite a task to solve manually. So no, I won't ask you to do something like that. Now, if you see a circuit like that, once we put in the element relationships, depending on what those are, great simplifications might result, to the point that the 16 equations could very quickly work out to be reduced to 5. In which case, if the numbers are not crazy, and I'm not asking for 3 decimal points and weird square roots and so on, then yes, I think we should be able to, with simple numbers, solve a system of 5 equations, 5 unknowns in 15, 20 minutes. You see? So that's the thing. So going back to the issue of the calculator, if on an exam so if for your homework questions, if you want to use calculators, fine. If for an exam question, I see that I've come up with something that I think is a nice problem, but I can't find a good way of having simple numbers so that heavy, serious arithmetics are involved, then I'll ask you to use a calculator. If not, then no need. I think the calculator will be a kind of waste of time. OK, anything else? All right, so KVLs and KCLs. This is an example, and we will do many more examples of this. So, obviously, I don't want to dwell on it for too long right now. And by the way, you can make this example into 3 other examples too, right? Go write the other KVLs, try to see which KCLs to combine to get which other one, and so on and so forth. Okay. So with that, I want to move on to the next topic, the circuit elements. Starting with the wire, which we talked about last time. The wire, just as a reminder. Oh, by the way, all these elements that we talk about, we will talk about a so-called ideal or simplified representation. So if we talk about a wire, we talk about something that has 0 resistance, really. Okay, any real wire obviously will have some resistance. But so for really something wrong here. For now, ideal or simplified, you might say, descriptions. So wire it's simply a 2-port element, has 2 ends. Voltage drop across it is always 0. It can allow any current, magnitude of current in any direction. Okay. Well, I won't say drop explicitly, 0 voltage. By voltage, we mean the potential difference between the 2 ends of the element, right? So the element voltage. So this V is simply 0, no matter what this current I is. It has 0 voltage for any value of current. I think next we had the switch on the list. Oh, sorry, too far. A switch is like that, and you might then close it. If the switch is closed, so if you close that gap, it becomes simply a wire. So 0 voltage drop, any current can pass through it. And that's, we all use switches all the time. That's exactly what it is, nothing special. If it's open, the current is 0. Okay? So for switch, if closed or also known as on. It's like a wire, so it has 0 voltage for any value of current that can pass through it. If open or off, I think perhaps it doesn't take much imagination to see that if the wire, the switch is open, no current can get through. Electrons can't go through. There is a big gap. As an aside, electrons can travel in vacuum. Okay, that happens all the time. But you need circumstances that make that happen. Okay, so in a regular switch, you don't want that to happen because something is going horribly wrong if the switch is open and there is still a current, right? You say something is arcing, something is wrong. Okay, so in an ideal and simplified picture, if a switch is open, it has 0 current. And I think here's an opportunity maybe to ask a quick clicker question. And again, these are not meant as an evaluation. Okay, so I just want to get feedback from you guys. So don't worry about getting the right answer. Which also means for me to get proper feedback, make sure it's your own answer. So don't consult, so that I know where the class is standing, how many people feel which way. Okay, so here is our clicker question. I haven't turned it on yet, so don't shout out the answer, please. Okay. So here is the clicker question. Let's hope this works. So we have 3 options. When the switch is open or off or disconnected, we said it has 0 current. What about its voltage? Is it A, 0, B, infinity, C, neither of those? So you have, there you go. All right. Here's the result. Let's take a look. So we have 50% of class saying neither 0 nor infinity. So, and I take it you're not saying it's going to be 5.3 volts, right? It's you're probably thinking that it could be anything, and you would be right to think so. When the switch is open, it's basically 2 points that are completely disconnected. There could be any voltage difference between those 2 points. It depends on what's going on in the rest of the circuit. Okay? It's 2 points that have no direct link. They have maybe an indirect connection through a bunch of other elements. They have no direct link. So it's kind of like the statement that I had on top. If it's closed or on or connected, it has 0 voltage. It's just a piece of wire. And any current can go through it, and in either direction. If it's off, it has 0 current. Obviously, nothing can go through it. And there is no voltage relationship between the two sides. So when it's off, it can have, so let me close this. pretty persistent. Okay. It has zero current for any value of voltage. And this value can be either way, positive, negative. There could be a voltage difference in either way. Okay? So this is how a switch works. I think I can erase this. By the way, about the clicker, like I said in my email, you know, if you miss an occasional class or occasionally the clicker doesn't work, don't worry too much. Like I said, if you have 80%, basically as long as you answer one clicker question per class, even if we have multiple ones, and if you answer during 80% of classes, you will get the full 5% of the clicker thing. This is not meant to be a tyrannical, you know, you have to be here every moment of your time. Okay. So a question here is, you know, there's maybe something about this that makes us uncomfortable. Can we say a little more than can be anything? The answer is no. And so the two sides are completely disconnected. It could perfectly work out that the rest of the circuit is such that the voltage difference between the two ends up being 0 by accident, just because of the rest of the circuit. So we don't know that it's not 0. 0 is just one value like any other value among infinite possibilities. You can exclude infinity, because if you had an infinite voltage, so you could assume that in a real circuit in the world, you won't end up with an infinite voltage. We will see maybe in a week or two in some examples where you could have situations where you risk having an infinite voltage imposed at some point, and you will discard it, or you will make sure that it doesn't happen, or you will know how to deal with it. It's hard to talk about it without specific elements. We'll see examples of that. But there is nothing about the switch that imposes either 0 or infinity or any other specific value. Okay. Was there a hand raised? Oh, okay. So that's the switch. Let's talk about the voltage source, and then we'll take a short break. Okay. So I'll first talk about what we call an independent voltage source, or well, let's be more general. A voltage source. A voltage source, an example is the battery in your phone, or the power supply that you worked with in the lab, the big box that I think most of you have already played with in the lab, where you got, let's say, 3 volts at the output. If you look at the battery, it has a fixed voltage between the two terminals, right? You buy a 1.5 volt battery, and that's that. The voltage is fixed. Okay? So a voltage source gives you a well-defined voltage with a well-known polarity. You have a positive side, negative side. You can trust the manufacturer on that. So we know that. A voltage source, and it's shown like this. Let's first talk about what we call an independent voltage source. And it looks like this. And it has a polarity. And let's say you call this Vs, as in source. Will give you a well-defined voltage. The palm recognition is not working very well today. What is the current? How much current does it give you? So here's one suggestion. Voltage divided by impedance, or you might say resistance. We are talking about an ideal or simplified voltage source. Any voltage source would have this concept called its internal resistance, and that would impose a limit on the current. But it doesn't tell you what the current actually is. it depends on the elements in the rest of the circuit. In other words, the current can be anything. So you can think of a voltage source as a generalized switch. It has a fixed voltage. It's non-zero. In the case of the switch, it was 0 volt. And it could give any current. A voltage source will give you a well-defined voltage, any current. For any value of current. So a voltage source actually does not impose what the current is. It's a very, if you want, it's an element that does great service. It says, oh, I'll give you this voltage no matter what you do. You can take this voltage and be comfortable and do whatever you want with it. I'll provide whatever current you want. Now let's put this into perspective. If I gave you a small battery, a 1.5 AA battery, and I said, here, I have built an electric plane that can carry 10 passengers, and its motor requires a 1.5 volt source. Here, a 1.5 volt battery, put it in that airplane, and go fly. Would you think it's going to work? That sounds too good to work, to be true, right? So what's happening there? The fact is that motor, sure, maybe it needs 1.5 volts. I mean, I'm just making this example up, okay? I don't know of an electric airplane that requires a 1.5 volt source and can fly 10 passengers. But let's imagine that's the case. But that motor surely would require a lot of power, right? Which means the product of voltage and current has to be very high. It's doing a lot of work, carrying a lot of weight. So the current has to be very high. You might say, oh, yeah, sure, maybe something like that could work, but surely it would require, I don't know, thousands of amps of current to get off the ground, right? Now, would you think a small battery like what you buy for $2 can give you thousands of amps? Thousands of amps is a huge amount of current. It won't. So there will be a limit. So a battery will have a limit on how much current it can provide. But up to that limit, it's supposed to be very well behaved. Okay? So there is a practical limit, of course, right? So we're not talking about exceeding that limit. So when I say for any value of current, of course, that has to be qualified up to a certain limit. And by the way, the same for a wire, right? If I gave you a thin wire and said put 10,000 amps through it, you wouldn't, right? So up to a practical limit. So when I say any, you know, maybe you'll put a warning sign here. We are talking about simplified ideal models. Okay? So that's what you call an independent voltage source. I think it's a good time to take a 5-minute break, and then we'll take it from there. Okay, so maybe we can restart. So quick question. How many of you have started working on the assignment? Okay. Okay, great. So this is, again, remember, for it to synchronize with your Canvas gradebook, you have to go through the web work link on Canvas. So sign up like that, and then access the assignments also directly through Canvas. And so if there are a few of you who are still not on Canvas because the registration is taking long, send me your, email me with your name, CWL, and student ID, and I'll try to see if I can add you somehow. I was told that it should be possible. Okay, so that way you will have access. But hopefully you will all be registered soon anyway. So the next element that I want to talk about is another variation of the voltage source. If the first one was called independent, you might guess the second one is called a dependent voltage source. And its symbol is a little different. It's a diamond. So it's still a voltage source. It provides a well-defined voltage difference, or voltage, or potential difference, between its two terminals. Okay? Except that the value of this voltage is not just one simple number like your battery 1.3 volts. For instance, it could be a multiple of some other voltage somewhere else in the circuit. Okay? In general, Vs is a function of some other quantity in the circuit, some other variable. Okay? So it's still the same thing. It gives a well-defined voltage for any value of current, but the voltage itself is a function of some other quantity. So this Vs in this case, instead of being 1.5 volts fixed, it could be, for example, Vs could be, let's say, 8.5 times some V1. And V1 would be the voltage across element 1 in your circuit. See? So in this case, Vs is just a multiple, 8.5 times V1, and V1 would be voltage of element 1 in the circuit, in a given circuit. Okay? This is just an example. In general, it could be anything. It could be a function of a current somewhere else. So this is called a voltage-controlled voltage source. So it's a voltage source that itself is controlled by some other voltage in the circuit. It could be a current-controlled voltage source, a voltage source whose value is controlled by some current somewhere in the circuit. And here's one way of implementing it as an example. In the lab, let's say you have your teammate, and you ask your teammate to measure a current somewhere in the circuit using an ammeter, and then you take the value of that current, multiply it by 3, and dial in 3 times that current into your power supply. So you have now created a current-dependent voltage source, human-mediated current-dependent voltage source. Okay? In practice, you can do these things with actual circuit elements. Okay? So we will see a lot of these things in examples. So right now, I'm just trying to give you, like build a Lego box where we have all the tools, and then we'll start putting them together. So similarly, we have current sources. We have independent current sources and dependent current sources. So a current source so similar to the voltage source, can be independent or dependent. An independent current source is shown like this. And it would have some current Is running through it. So I want you guys to think about, in analogy with a voltage source, what the definition or description of a current source is.
You didn't mention the current and the dependent source.
Say again?
What can the current be in the dependent voltage source?
For any value of current. It can be anything. So again, a dependent voltage source does not impose any value of current, just like an independent voltage source. It just imposes a voltage. It just so happens that its voltage itself is controlled by something else in the circuit. Okay? Could be controlled by a current, could be controlled by a voltage. And that's why you would call it either a current-controlled voltage source or a voltage-controlled voltage source. So a current source, very much in the same way, but it's, if you want, there is a duality here. A current source gives a well-defined current, in this case I sub s, in this direction from left to right, for any value of voltage. With the same caveat that there are practical limits, of course. You can't expect a small current source to be able to withstand a 20 megavolt voltage across it. A dependent current source is the same thing, except that the value of the current is controlled by either a voltage or a current somewhere else in the circuit. Let me just finish this. Its symbol is again a diamond. And gives a well-defined current for any value of voltage but the current itself is a function of some other quantity. Okay? Have a question there? I think. An example of a current source from this abstract point of view is something that when you put in the circuit, it forces, let's say, 3 amps going that way, okay, at the circuit level element. If you're wondering how you would make one in practice, very simple examples would be with a transistor, for instance. You can think of a simple circuit called a current mirror with 2 transistors. You can easily make one. And it's actually it basically relies on the properties of these active elements. So, and by the way, the same way for a voltage source, it's not a trivial element, right? If you open a battery, there is a lot of electrochemistry going on there. Or if you wanted to make a power supply, it's actually a circuit in itself, right? So in the same way, a current source is also a circuit. But from the outside world's point of view, it can be simplified. Was there another question somewhere? Okay, so voltage source, current source. Now I had a couple of other elements that maybe don't get as much attention. Voltmeter and ammeter. What does a voltmeter do? You already used some in the lab. Measures the voltage, right? It has 2 probes. You put it on the 2 sides of the element, and it tells you what the voltage is. A voltmeter is indicated by a sign V in the circuit. So a voltmeter, it could be the simplest handheld voltmeter. It could be a fancy multimeter that has multiple functionalities, voltmeter, ammeter, ohmmeter. It could be something more elaborate, like an oscilloscope. An oscilloscope is, in fact, a voltmeter. But it's a voltmeter that measures not just the value of voltage at one point in time, but it can follow it over a certain period of time and plot it as a function of time, right? So if you have a signal that's changing with time, a voltage signal that's changing with time, you wouldn't use a DC voltmeter that can just show one value, but you would use an oscilloscope. Okay? But again, from a circuit level point of view, it's just a simple two-terminal element that when you connect across 2 points, it will tell you the voltage between those 2 points. Now, what would you expect that the effect of the voltmeter on the circuit is? So I have a circuit, I'm doing experiments with it, and I want to measure a voltage. I put the voltmeter probe somewhere. What effect do you expect the voltmeter would have on the circuit? You would hope that it has no effect. It's purely a measurement tool, right? Now, of course, you know that any measurement will have some effect. But again, we are talking about a simplified or ideal picture, right? So a voltmeter tells us the voltage between its terminals without affecting the circuit. Which means it should not draw any current. So when you connect it to something else, whatever nodes and branches you had there, and they had voltages and currents passing through. Now, if you connect this, there should not be any current stolen from those branches to go through the voltmeter, because if that happens, it means the rest of the circuit has been affected. So it should be able to show you what the voltage is between its two elements without drawing any current. In other words, it should, or it does not draw any current. Its existence on the circuit does not change anything to the values of voltages and current in the circuit. It's giving you a set of eyes that can read voltages. That's all. Okay? An ammeter does a similar job for current. Tells us the current that's passing through it without affecting the rest of the circuit. And what that means, and this is something that we will perhaps feel better when we see examples, what that means is that it should not incur any voltage drop. It should have 0 volts between its two ends. And you will see that why in examples. So without affecting the circuit, which means it does not take any voltage. The voltage between its two terminals will be 0. If you wanted to think about the voltmeter and ammeter in terms of what their equivalent resistance is, the voltmeter is essentially a resistor with infinite resistance. No matter what the voltage is between its two ends, the current is 0. Because V is Ri, if R is infinity, no matter what V is, I will have to be 0. It's some number divided by infinity. An ammeter has a 0 resistance. So no matter what the current is that's passing through it, multiplied by 0 resistance, it will give you 0 voltage. So think of the voltmeter as an infinite resistor, a resistor with infinite resistance that just happens to have a dial that will tell you what the voltage is. That's all. And the ammeter as a resistor with 0 resistance that just happens to have a dial that will read the current that's going through it. So they are not supposed to affect the rest of the circuit. And we will soon see why they have to have this property of infinite resistance or 0 resistance in order not to affect the rest of the circuit. Now, a lot of the subtleties of solving circuits and a lot of mistakes that happen are because of missing critical points about these things. So what I'm going to suggest is that for the next little while, if you're solving problems at home or looking at examples in class, have what we did last time and today, the notes from last time and today, have them very handy as a reference that you can go back to very frequently so that you gradually get used to these. So these are not things to memorize, but things to start feeling in practice. And so every time we do an example, have these handy so that you can go back to them and check. Okay? Yes?
So why is it that the voltmeter has infinite resistance? Because if V equals IR, wouldn't that mean it has infinite voltage?
So the question is, if V equals Ri and R is infinite, does that not mean that V will be infinity, which we said is not a good thing, right? It will be unless I is 0, right? So in a voltmeter, V is a value, a finite value. I is 0, and R is a finite value divided by 0, which is infinity. Or I is a finite value divided by infinity, which is 0. So there's no contradiction. So next we had the resistor on the list. And we talked about this last week, so I'll just remind us. Oh, before that, one thing I want to point out here. When I showed a voltage source, I have indicated this Vs. I have not drawn a current here. But notice I said it can have any current. So just because I haven't put an arrow and said I, it doesn't mean it doesn't have a current, right? I wanted to emphasize the property of setting a voltage. But it does have any current. So don't be misled by the appearance that here I haven't shown a current, or here, or that here I haven't shown a voltage. It can have any voltage. So in a circuit, when you start solving things, of course you have to give a name to the value of the voltages here also. And similarly, for a voltmeter and ammeter, because you have to have a sense of polarity, again, you would want to indicate, if you say this voltmeter measured 5 volts, well, 5 volts which way, right? So you would have to indicate with plus and minus. So those things still apply here. I just didn't want to make this look too crowded. So a resistor we talked about it. It's defined by Ohm's law. At capital O. Ohm's law is saying that you take a conductor, you measure its voltage and its current, you divide the two, it's going to give you a ratio, and that ratio is not going to change if you change the current or voltage. They will grow proportionally. An ohm meter is something that you connect to the two sides of a resistor, and it tells you the value of that resistor. Okay? Again, it has two terminals. And again, I think in the multimeters you have in the lab, you can choose voltmeter, ammeter, ohmmeter. Okay, so we're just building up the Lego box. Capacitor and inductor. We alluded to capacitors last time. Let's just list them. So a capacitor, like a resistor, is defined by its current voltage relationship. And instead of a simple proportionality of the current being a factor proportional to V, the current is proportional to the time derivative of V. Okay? So again, to define the voltage and current, so if this is I and this is V, I equals C dV by dt. And I think we talked about this last time, so I don't want to repeat it, but it came from the fact that in the capacitor, charge was this. So current, which is the time derivative of charge, remember the rate of flow of charge. If the value of C was constant, if it was a capacitor that itself was not being affected, the value of which was not being changed, then you would simply have C dV by dt. Oh, and resistance is measured in ohms. What's the unit for capacitance? Farads. So C is capacitance. in farad. An inductor is the reverse. And the simplest physical implementation or embodiment of a capacitor is two parallel plates, if you want. And that's hence the symbol. The simplest embodiment of the inductor would be a coil, because you're using the magnetic flux that's generated because of the current through the coil. So if you have I and V defined like this, V is, and L is the value of inductance. What's the unit? Anyone remember? Henry. Do you guys remember things like Ampere's law and Faraday's law from first year electricity and magnetism? Who remembers anything about them? Okay. Yeah, okay. This circuit this course is not about electromagnetism, so we're not going to discuss those. The reason I mention these every now and then is for you to make the connections, that's all. Okay, so now, of course, if you want to have a deeper understanding of these things, it would be good to review those, but we do not go down to the level of why capacitors behave in this manner and why inductors behave in that manner. That's what you did in your physics in the past. Okay. We've covered a lot of grounds. If I go back up here, gone all the way down to here. The next element is the diode and op-amp and then transistors. These are, like I said, what really constitute the topic of the second half of the course, which is, in fact, formally, it's called electronics. It goes beyond simple electric circuits. That's what you call electronics. The moment you start talking about diode and op-amp and transistor, that's electronics. We will do a quick overview of them ahead of time, so we don't have to wait for the second half of the course. But I'd rather, at this point, in the remaining time that we have, do a couple of examples with what we already have got, okay? So with basic electric circuits. So with resistors, capacitors, inductors. So we'll now take a break from describing more elements and take a look at how to put some of these elements that we have already reviewed together. Okay? Solve this circuit. Now we see a real circuit with real elements. Solve this circuit, which means find all the voltages and currents in the circuit. So I'll spell that out. So let's see if, so I'm asking that you guys try this on your own. And again, feel free to discuss, consult. Because we've got only 5 minutes left, let's take a look at it together, and then hopefully you can continue working on it at home. Well, first of all, let's just make sure we give names to these voltages and currents. Fortunately, for the source, things are easy. We already know the voltage. We don't know the current through this voltage source, so I'll call it I1. This resistor, let's call this I2, and V2. This one, let's call it V3, and I3. And this one, V4 and I4. For the source on this side, I know the current, 2 amps going up. I don't know the voltage, so let's give that a name. V5. So you might already say you know your V1 is 5 volts in that direction, and you know your I5 is 2 amps going up. Okay. So writing the KVLs, here's one loop, and here's another one. I'm going around this loop, starting from the bottom left. The first side that I encounter is plus. So that 5 volt, I'll include it with a plus sign. Plus 5. Then I encounter V2 with a plus sign again, and V3 with a plus sign. Second loop. If I start from the bottom left, for no reason other than my personal preference, I encounter V3 with a minus sign, and then V4 with a plus sign, and then V5 with a plus sign. And that's it. The third KVL, which would be around the big loop, is the sum of these two. So then KCL, I have one big node down here. If you look at this, this is all connected. This is just one big piece of wire. Then I have another node here, and then another one here, and another. So there's 4 of these, and I get 3 independent equations. So up here, for instance, I'd have minus I1 minus I2. So if I call this node 1, node 2, node 3, at node 2, I have I2 going in, I3 leaving, and I4 also leaving. So I have, plus I2 minus I3 minus I4. Call 0. And at node 3, I have I4 going in, and the 2 amps also going in. So it's plus I4 plus 2 amps equals 0. And I won't include the unit we are working in the international system. And finally, the element relationships. If you look, I have already included what I know about the sources. I have already included the fact that the voltage by this voltage source is 5 volts this way, and the current by this current source is 2 amps that way. So that's already implied in my equations. So that's trivial. If I wanted to really be to elaborate, I would have called this V1, and then separately I would have chosen to write an equation V1 equals 5 volts. But it's already embedded in those. So I have just the resistors left. V2 is 2 times I2, V3 is 1 times I3, and V4 is 1 times I4. So all right, how many equations do I have? 8. How many unknowns do I have? 8, luckily. Otherwise, we would be in big trouble. In fact, otherwise, we would have made a big discovery that there is something fundamentally wrong with the science of circuits. So it would have been very exciting. Unfortunately, no such excitement today. So this is your system of equations, 8 equations, 8 unknowns. Now, I didn't particularly work on the numbers here now to make this something that does not end up with fractions. So you can go practice solving this and see what you get. But more importantly, please go repeat this exercise at home, go through it, and maybe try to write the big KVL also, try to write the KCL down here, see that it comes out of the existing KCLs. All those things that we talked about, practice it on this. OK? Thank you.